Our final section of Chapter 5, we've got the average value of a function. We know how to find the average of a bunch of numbers. You just add up that bunch of numbers and divide by however many numbers you added together. So if we want to find the average temperature for a certain day, maybe, what would we do to compute the average temperature? Well, let's see, I'd probably add the hourly temperatures, 24 hourly temperatures. And then divide by 24. And if I could be more accurate, I guess what I'd do is I'd just bump this number up and add every 15 minutes or something manageable, I guess, and divide by, well, a larger number of readings, and I'd improve my accuracy. Well, if we've got a function, we are going to add up the value of the function in a bunch of different places. And then we're going to divide by however many places we had found the value of the function. So that's how we're going to find average value. Now, in calculus, we actually have a more efficient way of doing that. The average value of a function can be found if we're going to find, let's say, we've got 1 plus x squared. That would look something like this. And what is the average value starting at -1 and ending up at x is 2? All right, looks like, the value here I think is going to be, it's going to be 2. Put a -1 into our function here. And then that value comes down and it's less than 2, it's down to 1, and then over here I think it gets all the way to 5. And if we add up all of these values and divide by however many values we have, we'd find the average value. But in calc, what we can do is we're going to take 1 over b minus a. 1 over the end of the interval minus the beginning, and then we're going to multiply that by the area.
Extension 8458, Dave Malum, 8458. Thank you.
The area under the curve. And that's going to give us the average y value that we achieved between those two x values. All right, so it's, actually, it seems as if we're adding up an infinite number of values here and dividing not by the number of values, but if this thing were a rectangle, and we'll talk about the rectangle a little bit. Let's just plug in our numbers and see what we get here. Let's see, 1 over 2 minus -1 integral of 1 plus x squared dx. And I'm going to evaluate this between -1 and 2. I could do this without a calculator. We'll do it with a calculator. This is chapter 5. I said you can use a calculator anytime you want. So let's try this. 1/3 times the integral, -1, 2, of 1 plus x squared. So I'm hoping you're doing this on your calculator with me. I get the value is 2. So what that means is that this value right here this value of y equals 2, that's the average value of the function. Now, what that means is, and this is 2 right here, what that means is that this area right here, the area of this rectangle, formed by the average value, and the area under the curve, which is this red area, that those areas are identical. So if I can find the area under the curve, if I can find the area of this red stuff and smash it down into a rectangle, it's the height of that rectangle. It's the height of that rectangle that's going to be the average value. And I know that the area of a rectangle is the base of the rectangle times the height. Well, that means that the height of the rectangle is equal to the area divided by the base, or times 1 over the base. Now, we find the area using that. And this is 1 divided by this base of the rectangle. B minus A is the base of the rectangle. So that's all great. And this is a pretty easy formula to remember. But that's where the average value of a function formula comes from, and one that you need to remember. Expect to see this on our next assessment. Expect to see it on the AP exam one time. Pretty easy one to remember. Should be one we're prepared to attack. Now, if the function is continuous, and that last one was, it's preferable, then there exists a value c such that this thing's true. Now, what does that mean? Well, that means that there is some x value in that interval where the y value is equal to the average value. Okay, now the geometric interpretation of this. So we're going to be searching for this x value where the y value at that x is equal to the average value. Same thing we just talked about. We got this curvy guy. We're going to smash this thing. We're going to smash it down. We're going to smash it up. We're going to form a rectangle out of this. And this height of that rectangle, this y value, that's the average value. And what this mean value theorem for integrals says is that somewhere in this interval, as long as this is a nice continuous function, somewhere there's an x value where that average value actually occurred. So that's what we're going to be in search of. What is that x value where the average value occurred? If we go back to the previous slide, was there an x value where the average value occurred? Yeah, does appear to be, because this red guy was a nice continuous function. So let's take a look at this. If we've got the same function on the same interval, let's find that magical x value where the y value at that place is equal to the average value. Well, let's go like this. F of C. Well, if f of x is equal to 1 plus x squared, f of c is equal to 1 plus c squared. So 1 plus c squared is equal to the average value. Now the average value was 2. So I can subtract 1 from each side, and I get c squared is equal to 1, which means that c is equal to, well, the positive or negative square root of 1, which is positive 1 or negative 1. If we go back and take a look, did it appear that this blue line right here actually did hit red when x was negative 1? And it's pretty believable that this x value right here was positive 1. So we have found the x value at which the average value occurs, and that is the mean value theorem for integrals. And don't feel like you have to turn this into a C. Could I have said that f of x, 1 plus x squared, was equal to 2. X squared was equal to 1. And so x, that magical value, where the average value and the value of the function are the same, is positive or negative 1. Yeah, you can keep that in x. You don't have to call it a C. You're looking for that x value. All right, final slide. Show that the average velocity of a car on this time interval is the same as the average of its velocities during the trip. Good. We're going to show that the average velocity is equal to this. Now we're going to use average value of the function. Okay, this is final position minus initial position divided by change in time. Like if I'm driving up to a Packer game. When I get up there, my odometer probably says my final position, 120 miles, minus the initial position when I was in my driveway, which was 0, divided by, well, when I get there, it happens to be 2 hours after I started, which was a time of 0. So if I drive 120 miles in 2 hours, I think my average velocity is 60 miles per hour. Now, let's show that that's the same as this. All right. So, let's see. What is the integral of velocity? Let's see. I'm going to have 1 over t sub 2 minus t sub 1. And the integral of velocity is position evaluated between 1 and 2. So I'm going to have 1 over t sub 2 minus t sub 1 times, I drop this guy in here, and I get the position at a time of 2. Minus what I get when I put this in here, which was my position at a time of 1. And so the average value of all of these velocities, the average of all these infinite number of velocities is going to be equal to s at a time of 2 minus s at a time of 1 over t sub 2 minus t sub 1. So yeah, by adding all of those infinite number of things up and averaging them together, I'm going to get the same as if I just took final position minus initial position divided by the change in time. Now, I have a chance to practice some of these skills on the assignment that's in Schoology and realize that average value of a function and being able to find when that average value occurs is going to be an important skill when it comes to semester exam testing and AP testing. So let's be ready for that.